Okay, so this next question is about taking the logical form and writing those in terms of words if the two propositions are spelled out. So proposition P is that X is wearing a Rolex watch, and Q is X is a fashionista. And all you have to do is you have to interpret what's written here in terms of words, okay? In order to do that, you have to know what each symbols are, right? What does this symbol mean?
Implies.
Implies, right? P implies the other one. Or you can say if P then Q. That's another way to say it. I'll go with that. If P then Q. Yeah. What does this wiggle mean? It means not. Okay, so it's the opposite statement of this. So if Q means X is a fashionista, then this wiggle means X is not a fashionista. So this statement will be if P, which is if X is wearing a Rolex watch, then, so this if then corresponds to this arrow there. Okay. Then X is not a fashionista. Okay. B, what about this one? Not P and not Q. Okay, you just say, just stick in the not expression for each one of them. So X is not wearing a Rolex watch. And what is this symbol? What is this symbol? And. So put and. X is not a fashionista. Okay, so it's rather simple. It's not that complicated. If you have any questions, you can ask now. If not, I'm very sorry. Okay, number 5, you have to prove that P implies Q is equivalent to not Q implies not P. And this is somewhat clear if you look at real world examples. So let's say if you smoke more than 12 cigarettes per day, then you get cancer. Then what does this mean? If you don't have cancer, that means you did not smoke 12 cigarettes per day. If the previous one is true, then this should be true as well, right? Yeah. So they are equivalent, and in fact, this has a name. This is called a contrapositive of this statement, and often this is used for proof by contradiction. So let's say you have some mathematical theorem you want to establish. For example, an isosceles triangle has the same base angles. If that's the statement, you can write it as like, if a triangle is isosceles, then the two base angles are the same. To prove that, you can prove the contrapositive, which says, if the two base angles are not same, then the triangle cannot be isosceles. Yeah. And proving it that way, that's called the proof by contradiction, okay? So that happens frequently in the world of mathematics. But here, we're just trying to show that these two are equivalent, and when you're trying to show that two logical symbols are equivalent, all you have to do is build a truth table and show that they have the same value. So it's not that bad, it's quite simple. You just say PQ, true, 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 false, false, true, false, false. Do that. And then P implies Q. And then you probably want to put not Q and then not P. And then also do not Q implies not P. I mean, these two columns are not necessarily needed, but if you have it, it's easier to fill in the others, okay? All right, so P implies Q. If it's TT, what is P implies Q? True or false? True. If it's TF, P implies Q gives you?
False.
False. If FT, P implies Q gives you?
True.
True. FF, P implies Q gives you?
True.
True as well. See, the way I explained it in class is that P implies Q is a statement about what happens when P is true. It doesn't care what happens when P is false, right? I talked about like if you get 1550 in your SAT, you can get into SUNY Maritime College data science major, something like that. Yeah. But that doesn't mean there are other ways to get in, right? Yeah. So if a student does not meet 50-50, then it doesn't matter. Yeah. Okay. Okay, but now let's do not Q, not P. So this, if you just take this entire column and take the not, and everything will reverse, right? So it'll be false, true, false, true. Here it's not P, so I'm going to reverse all of them. So it's false, false, true, true. Okay. And then when I fill this in, this implies that. And first of all, if not Q is false, I don't care about what P does. It's if you start with an implies that the beginning is false, it's always true. That's how it evaluates, right? It's this, and then if it's true, then it better be true in order to be evaluated as true. This is the only case that implies will evaluate to false, right? Now compare the two columns. They're exactly the same, right? So you've shown that the two things are equivalent.
Which on the test, do you need to write anything or should you just show this graph?
That's it. Yeah, just put this table and you're done. Yeah. It's quite straightforward. Okay. Now, number 6 is pretty much the same thing. So let me skip number 6. You can try to put that, build your own. So let's go to 7. 7A. A union B A intersect B is equal to A subtract B union B subtract A. How do you establish this? Well, you can use Venn diagram to show this. This is the most generic Venn diagram if you have two sets, right? Okay. And what is this? A union B. That's this much, right? And then what does this mean? You're subtracting off the intersection. So if you subtract off, what do you end up getting? Only this portion. Agreed? Yeah. So that's what this left-hand side is describing. Let me try to draw the right side here. So the right one first has A and B. So what is this? A subtract B, right? A subtract B is this one here. And then what's the other guy? B subtract A is the other guy, right? B slash A means you subtract away A from B. So this is what you get. And then you're doing a joint, right? You're taking the union, so you're putting them together. So what does that leave you with? That's what you get, right? And the end results are the same, right? This is the end result. This is the end result. And they give you the same thing. And this is known as the symmetric difference. I mean, for me, this is more intuitive and the better way of showing that the two things are the same. And of course, in order to convince the reader, you should really, just writing the final answer is not enough. You should really write down the intermediate representations to show the reader what's going on for that to be a convincing proof. Now, you could also make a truth table to do the same thing. So let's say A, B, A union B, A intersect B, and then A union B minus A intersection B. Okay, and then A, E, B, A B union B, A. Okay. And then you assume, for example, let's say an element, there's an element in U that belongs to A and also belongs to B. In that case, does that belong to A union B? Yes, right? Does it belong to A intersection B? Yes. Now, does it belong to A union B minus A intersection B? Well, because it belongs to here and there, you've subtracted away, so it's no longer there. Does that make sense? So since that element is in here and that element also is in here, and you're subtracting away, that element has disappeared. That's how you think about this. Now, how about A subtract B? Well, because X is in A and also X is in B, something that's, if you have an element that's in the overlap, right? If something is in here, does that belong to A minus B? Yes or no? Here, saying TT means it's an element that belongs to both A and B, right? So when you do A minus B, does that X belong to A minus B? You don't know?
What X?
So TT means there's an X which belongs to both A and B.
Okay.
Okay? Now the question is, in that case, that same X, does that belong to A minus B? This X. No, the answer is no, because what is A minus B? A minus B is the collection of these guys right here. Right? This one, it will not contain things that belong to both A and B. Right? So that's a false. And for the same reason, this is false, and if you union both of them, it's false.
So A minus B would only be the A side?
A minus B will be only, this will be A minus B.
Okay.
A minus B. Yeah, you take A and you take away the things that belong to B, so you just have this much. Yeah. Now, if this is not so clear, then another way to say it would be this means, so if you have A not B, that's really saying X is in A and X is not in B. That's what it means, right? This is a collection of X is in A and X is not in B, okay? And then if you get that definition, then think about this. This means X is in A, this means X is in B. And now look at this statement. Is X in A? That's true, right? Is X not in B? That's false because we said X is in B, right? And then if you have true and F, what does this evaluate to? False, right? This evaluates to false. So that's why you can put an F here. Okay. Same thing here. What does this mean? That means X is in A union B and X is not in A intersection B. Not. Yeah. To subtract away another set means you're collecting the things that's in the first set but not in the second set. That's what this minus that means, right? But we already established that X is in both. So this is true and this is also, this is true and this is false. And again, you're doing and, therefore it's false. Is that okay? And then you go TF. In that case, this is true, that's false. Yeah, this means X is in A and X is in B. It's an AND operator, but since you have T and F, if you do the AND, it'll be false. Okay? But now you subtract T and then T minus F is just going to give you true, right? And then over here, if something belongs to A but not in F, then this will be okay. On the other hand, this will be not okay, but if you take the union, that's true. FT would give you true, false, again true. In this case, it would be FTT. And then when you have FF, both will be false, so it will be false. And this will be false and false and false. So you can use the true and false this way and establish that they both evaluate to the same true false values. So that's another way to show that the two sets are the same. Okay? Yeah, I think most people will find the Venn diagram method easier. Okay. We only have 10 minutes, so let me move on to 8.
I tested on Wednesday, right?
So if you want me to solve some more problems on Monday, you can. I plan to cover something new on Monday. If you review it during the weekend and you find something challenging, then we can do that again. Let's try this one. Okay, first of all, what is A cross B? That's called the product set. What do we collect? We collect all the ordered pairs with one element from A and one element from B. Right? So you can have -1, 0, -1, 3. You can have 3, 0, 3, 3. You can also have 4, 0, and 4, 3. That's it. So that's the product set. What about P of A? P of A is set of all subsets. And remember, when you talk about subsets, you should always include the null set. And then you have singletons, -1, 3, 4, -1, 3. Now it's a subset with two elements. And you should always include the set itself. So the -1, 3, 4. Okay, so that's every element in the power set. Okay, then what about P A intersection B? Well, first, what is A intersection B? What's the set you get if you do the intersection? This set and that set. What's the intersection?
3.
3.
Just the 3, right? Just the 3. Oh, okay. So in that case, what are the subsets of this? Null set should always be included, right? What are the singletons? Just that itself, right? You can't think of anything more. And that's it. There's no more. You can't think of any other subsets than the null set and the 3 itself, right? So that's the answer to E. Okay, last question is a word problem. It takes too long to write it, so let me just read it. Suppose U is a set of all students at Richmond All Boys High School. F is a set of all students in the football team, so you have set F. And S is a set of all students in the soccer team. B is a set of all students in the basketball team. And it says this, number of U is 235. Now, U is the set of all the elements in the context. So in this context, since F, S, and B are boys in the high school, so this must be the number of boys that are in the high school, okay? Some might be in one sports team, some might be in two, some might even be playing all three, and some might not be playing any sports at all, okay? So all of them are included in this U, set U, okay? So pictorially in the Venn diagram, you can think of it like this. You have U is the entire school, and there's the F, and then S, and B. I just realized FSB is, no, okay. Is that like something like KGB in Russia? There's another FSB? I feel like there's something like that, okay. Okay, so now what? It also gives you these information. Number of F is 79. Number of S is 92. Number of B is 101. Number that's F intersect S is 17. Number that's S intersect B is 28. And the number F intersect S intersect B is 4. Okay. So this is the case when somebody's playing all of the sports. And it seems like there are 4 boys in here. There are 4 boys who are very athletic and will play all the sports that's available. Okay? So that's the given. Now let's think about the first question. It reads, find the number of students that are in the basketball team but not in the soccer team. So A, what does that mean? It's the number of people in the basketball team but not in the soccer team. That's what it is, okay? Now, can you shade that area here? Someone that's in the basketball team but not in the soccer team. So it's like this. You have it's in the basketball team but not in the soccer team, so we're only taking this portion. Now, if you look at that picture, it's obvious that the way you get this is taking the number of people in the basketball team and subtracting the number of people that play both in the basketball and the soccer, right? And because the number in the basketball is 101 and soccer and basketball is 28, subtract that and you get 73. Okay. B, find the number of students that are in the football team or the soccer team. So it's number of people in the football team or the soccer team. Now in that case, you have football and the soccer, and you want to know the total thing, right? Now how do you get such a thing? This would be number of people in the football plus number of people in the soccer. But if you do that, then overlap is counted twice. Do you agree? The overlap is counted twice, so you have to subtract them once. So that's going to give you number of people in this F is 79. Number of people in the soccer is 92. And you have to subtract F intersect S, which is 17. Okay. So that's going to be 75 plus 79, 154. Now, find the number of students that are not in any of the football, soccer, or basketball teams. Okay? So what you want to know is C, number of people that are in the school but not in any of the F union S union B. Okay? Yeah. And that means that you need to get the number of people in the everyone minus number of people in FSB. And for this one, it's a bit complicated, but then we learned this formula. So let me recall this formula. If you have three sets, then A union B union C is number in A, number in B, number in C. But then if you do that, overlaps are counted twice, so you keep subtracting the overlaps. But then if you do this, then you've subtracted away the place that's overlapping from all three. That part completes gets disappeared, so you have to put them back again. So this is something that I proved in the last class. So hopefully this is okay. And we're basically doing this, but with F, S, and B. So let's use the above formula to find number in the FSB, which is you first add up all the numbers, 79, and somebody get a calculator ready because this one, it's beyond my ability. And then you have to do FSSB. Oh. Gee, I forgot to put a value for one of the intersections. Oh, yeah, it's here. FS. There's FB that's also given that I forgot to write here. This is, oh, sorry, this is 17 and this is 28. So my previous answer to the previous answer to part B is wrong because I quoted the wrong number. I'm sorry. But anyways, I have to do, oh, so everything's wrong. 20. No, this is 23. So this is 23. That's okay. That's good. Okay. So we have to do minus 23, minus 17, minus 28, and then add back 1. Okay. Can somebody do this for me?
Two
208. Okay, and then you do 235 minus 208, which gives you 20. What is it? 27. So there are 27 students in the school that's not participating in any of the sports. Okay, so that's the answer to C. All right. Okay, sorry that I wrote down the wrong number, so the answer to A and B might be wrong.